and we are discussing about confirmatory factor analysis, and that's continuation from previous lecture, so that's why I call this lecture as lecture number 2. Before we would go back into our example and we would recompute our results, I would like only briefly recap some rules in structural equation modeling that are mainly related to Cfa model. So rule number 4 is saying that all factor loadings are estimated if the theory doesn't expect that some loadings are 0. And once again, and I can show you our previous example. So here it is, left-right scale and liberal conservative scale. So according to this rule number 4, all loadings, so it means also this one, this one, this one, this one should be included. But according to the theory, which is trying to divide these 11 items into 2 factors, so we do not expect to have these cross loadings, and we have only 5 loadings from first factor to first 5 items, and then 6 to next 6 items. So that's it. So usually we expect that one factor is related only to one item. So that's classical model. Sometimes also cross loadings are applied in some special models, but we wouldn't go into this discussion. So that's all about this rule number 4. Rule number 5 is saying that if we have some model, then endogenous variables, so in our case, these are mainly these individual indicators, A47A up to A47K. So for these endogenous variables, there is no chance to estimate variance. And there is also no chance to add covariances for these endogenous variables. So it means it is impossible in structural equation modeling to make correlations or covariances between endogenous variables. Of course, you know, and it was, if I remember well, rule number 1, that for exogenous variable, I expect to estimate their variances, and I usually by default expect that these exogenous variables are related. So that's just opposite rule, I would say. And rule number 6 is saying that if you have some latent variable, so here we have mainly these 2 factors, LR and LC, so then we need somehow to set up the scale for this variable, as it is, I would say, totally artificial variable with no scaling at all. And there are 2 options in GMOV. The same options are applied in other packages. So it means you will find the same option in JASP as well as in AMOS, Srmr, UQS, or M+. And these options in GMOV are present here by options. And here on the right side, there are 2 options. You can set up factor variance to equal 1. That's default in GMOV. And you can, and that's what we decided to apply, ask that factor should be scaled by the first indicator. So that's why you can see on this picture, this dashed line, which is saying, okay, here this length and here this length to the first indicator is set to the value of 1. So that's alternative setting up the scale of latent variables. And I would say that this is the most common settings for scale of latent variable. So that's why we change default in GMOV. So these are 6 rules, or at least rule number 4, 5, and 6 for CFA. And I would go back to our computation. And last time we applied 2-factor model. And once again, we have 11 items. And my decision is that I would like to say whether this model with no relationship between factors and this picture with relationship for 2 factors is better for my data. So I would like to evaluate the difference between these two models. And last time we were successful to evaluate this model. I will briefly go through these results. And if I remember well, we concluded that this model, so it means model with correlated dimensions. So once again, that's left, right, and liberal conservative scale, seems quite good according to different criteria. And we would go to model which is slightly more simple. That's from statistics quite easy to guess, as there is one link, one correlation or covariance between factors missing. And we would try to evaluate whether this model is better than previous one or not. Unfortunately, in Jamovi, there is no chance to ask for this model with uncorrelated factors directly by the dialog of confirmatory factor analysis. So there is no chance to change it. If you would switch into CHESP, there is one option by which you can differentiate these models directly in confirmatory factor analysis dialog. So sorry for that, that in Jamovi it's not present. But we know that all structural equation models can be prepared by SEM syntax mode. So that's why currently we would switch into SEM syntax mode, and we would use description for model with uncorrelated factors. It's quite strange, but it is following basic logic of structural equation modeling that usually models that are expecting that there is no relationship between exogenous variables, and factors are also exogenous variables, are usually slightly complicated by syntax. So it means you need to write more, and usually model with related exogenous variables, so it means with related factors, are usually easier to prepare. So that's based on the rule that usually it is expected that exogenous variables are related. So I will open Sem Syntax window. And before we would go further, I would like to say one short comment, or I would like to say one very important warning. If we would follow this data and we would prepare the model, I will share with you comments. So it means 3 rows of comments for our model with unrelated factors. So if you prepare the model and if you run it, Jamovi, according to my previous experience, will give you some error message, and this error message is very, very strange. There is something like that you should switch into standard estimation, but usually by default there is standard estimation here. Here it is, standard errors and standard estimation. So that's quite strange, but as I try to inquire what is behind this problem, so there is one problem which causes this difficulty. So if you go back into data, and that's quite inconsistent across individual procedures in Jamovi, this general structural equation models procedure is expecting that all your variables which will be present in your model will be cardinal. And if they are not cardinal, Jamovi will not give you any result by default. You know from previous lecture that for confirmatory factor analysis dialog, there was no problem, but for general SEM, it's not working at all. So the first step before we would go further is that we would need to go through all these variables, A47A up to A47K, and you need to redefine the scale to cardinal. So if I double click to the variable, and here I would change measuring type to continuous and go to next variables, then it would be possible to apply structural equation models, or in our case, that's only confirmatory factor analysis with unrelated factors. So here it is. So 11 times necessary to redefine the scale. if I remember well, in JESP, it's slightly more consistent. Only continuous variables could be applied in both procedures. So it means SEM general and CFA. So here is the last one. And currently, as I can see, all my variables, A47A up to A47K, are defined as continuous. So it means it should be, I hope so, possible to estimate the model. So that's the first step, which is necessary. And next step is that we would need to describe the model. So it means to set up equations or syntax for this model. First of all, I will show you how we should prepare this model by writing. Then I will share these together. So if you have two factors, so first of all, you will add some names. So for consistency, I would apply instead of F1 LR, and for the F2 LC. And you can see that measurement model, sometimes CFA is called as measurement model, as I'm trying to measure something behind by indirect observations of some variables. For Latent language, you need to type equality sign and then tilde. And by this, you are saying left, right, I am measuring by the set of items which are on the right side of this equation. And then, very simple, you will only add individual indicators, so A47A up to A47E for the first factor, and pluses must be between individual indicators. So that's definition of the first factor. And for the second one, this is nearly the same, only I'm defining LC, and once again, equality, tilde, and the set A47F to A47K. And if I like to have unrelated factors, I would need to type that LR as the first factor is correlated or by covariance to LC by 0. So technically, and we know about it from correlation example at the beginning of SEM lectures, I need to type LR double tilde 0 times LC. If I would compute model this relationship between factors, this part of command will be missing. So now I will copy this into the chat. I will stop sharing for a minute and find the chat window. This, and here it is for your own usage. So once again, sharing the screen, and I will copy and paste once again these commands into this window for structural equation modeling. And before we would run these commands, I would like to go into model options. And here you can see that there is some automatic selection of estimation method. We wouldn't go into details, so we can skip it. For parameter options, you can see that by default, you will estimate standard errors by some standard, so it means maximum likelihood technique. And there is also some alternatives such as robust or bootstrap, which are flexible if your data are not perfectly normally distributed, etc. But for us, the biggest importance part is here, the scale / standardized variables. And you can see that by default in this Sem syntax module, settings for the scale of latent variables is based on fixing to the first indicator. So once again, it's slight inconsistency. As in CFA, it was fixed variance to 1. And here for SEM, it's fixing to first indicator. Once again, this is the most common option. So that's why here we would use this default. And you can also ask for standardization for all observed variables, but it's not necessary, as we can also see standardized results together with unstandardized. So it's not necessary for us to ask for this out. So that's about parameter options. We will skip the next option, multi-group analysis. We will go into this section later for multiple group confirmatory factor analysis, so we don't need it. And I would go to output options, and I will ask for additional fit measures at least. We can also ask for residual covariances. And we can also ask for modification indices, as we know, at least from well-being example, that sometimes these modification indices can help you to advise what should be possible improvement in your model. So these residuals and modification indices are especially useful, and they can help you to find the problems of your model. So that's output options. And finally, we would like to check whether our path diagram is correct or not according to our expectation. So I would ask for path diagram. Here, that's quite nice. You can ask for showing residuals. So we can ask for this option. And I would ask, this is the best output according to my opinion, that passes should be individual betas. So it means standardized coefficients. So that's about this path diagram. And the last step would be that we would run this model. So if we copied these 3 rows of commands into this free window, so you can click here to run. Or alternative, as you can see here, Control plus Shift and Enter is possible combination of keyboards. So here it is. I hope it would work. Once again, if we didn't redefine variables into continuous, this dialog wouldn't be active, or there will be some warning and no results would be available for us. And we would like to evaluate this model and compare the model to the previous one. So once again, here we have 2 competing models by pictures, and we would like to see which one is better for my data. Before we start to evaluate this current model, I would go back slightly to our previous discussions. So it's still recomputing. So I would maybe go further and evaluate this model. Maybe in a few seconds it will be fixed as we changed the scaling, and it should be available here, but not on my JESP, unfortunately. I don't know why, but here we have at least some values. No, still not. Okay, so I would go first of all to our model, which is present here by picture. And you can see that here LC and LR are not related. As you can see that for the length, there is 0 correlation or 0 covariance. We can also check individual factor loadings. And once again, there is dash style for those items that are setting up the scale factors. So this is still the same. And once again, we can see that for first set of items measuring left and right, these factor loadings are slightly higher than factor loadings for liberal and conservative scale. So once again, measurement of liberal conservative scale is slightly worse in comparison to left and right scale. So that's the same story as previous. And if I try to evaluate the model, and then we will try to find some problems of the model. So first of all, we can go briefly to chi-square test. So this is our user model. Chi-square is 449 with 44 degrees of freedom, and p-value is extremely low value. Once again, we know that this test, so it means chi-square test for social equation models, is not very useful for complex models, so we can skip it for simplicity. And we can go to fit indices and then additional outputs that are present here. So maybe I will start with these additional outputs and measuring of fit of the model by especially CFA and TLI. And both of these values, as you can see, are quite low. Previous model, if I remember well, CFI was slightly above 0.9 and TLI was approximately 0.9. But currently 0.83 and 0.79 is saying, okay, maybe there is some problem in your model. So that's about CFI, TLI, and you can see all the rest of these alternatives are quite low, usually, once again, for benchmark, we are using the value of approximately 0.9. And if I go back to fit indices, so we can also check Srmr and Rmsea. And once again, recommendation for Srmr usually below 0.05, for Rmsea below 0.08. So only Rmsea is quite good enough, but for Srmr, it is approximately 2 times higher than it should be for quality model. So it seems that according to all of these criteria, and we will not go into other details, it seems that my model is not very good, and at least in comparison with previous model, it is much worse. So my GMOV is still computing results. So sorry for that. It will not be possible to check previous model in detail, but we can go to the next set, and maybe then I can recompute previous model by only changing this condition that both dimensions are uncorrelated. So I will run SEM model once again. But let's go down to our description here for outputs. And here we have modification indices, somewhere at the end, and also residual covariances and residual correlations. It is written here that residual covariances are here in lower triangle, and upper triangle is created by residual correlations. And ideally, once again, these values should be as small as possible, ideally at least below 0.1. And you can see that some of these values are not so nice. For example, for A47F here and A47D, there is quite big residual correlation. The same big values are here, etc., etc. And we know, or at least we can expect, that these quite big residual correlations across dimensions are maybe caused by the fact that correlation for dimensions, so it means for factors, is missing in my model. So that's my assumption. I can go down to modification indices, and you can see this previously discussed assumption in reality. So this table, which is nicely sorted according to the value of modification indices, once again, modification index is nothing more than difference for chi-square test criteria for model, which will include some more parameter and which is not including this parameter. And you can see that the biggest value of modification indices is that you should add relationship for latent variables. So it means left, right, and liberal conservative scale. So if you add this correlation or covariance, as you can see double tildes here, so your chi-square would decrease by nearly 200 units. So once again, if I go back to my current chi-square test, which is approximately 450, so it would decrease by approximately 200 units if I would add only relationship for these two dimensions. So no zero, but I should add some relationship for these two dimensions. That's what is modification index table recommended in the first step. And once again, if I can see the biggest value for modification index, I try substantively decide whether I should add this parameter into the model or not. And here it is saying, okay, left and right and liberal conservative should be related. I would say, yeah, maybe they should be. And we know that the result will be quite impressive, that correlation would be finally approximately 0.6. And here it is also written. Here at the end, there is something what is called in GMOV SEPC, and in brackets, there is shortage all, and it is nothing more than estimation what will be correlation. So it means standardized estimate of covariance for relationship between left and right and liberal conservative. So from substantive point of view, that's very, very big value. And that's why maybe I would decide to switch into different model. And that was my goal, to differentiate these two models. And at least currently we know that this model is much better than previous one. And once again, my GMOV has some problems. So I would once again run the model with related factors. So I would run only first two rows from our command. So I would ask once again for Sem Syntax. Here it is. So here it is. I would only change options. So to see path diagram with residuals and betas, I would ask for fixing. That's correct. And I would ask for additional fit measures. I would try to run it. And you can see that according to our expectation, current chi-square is 232. So it decreased a lot by approximately 190 units, as we know from previous discussion. If you can see Srmr, Rmsea, quite low values. For Cfi and TLI, quite nice value, 0.922, 0.9. And last one, if we can evaluate the relationship according to our previous SEPC value, it is approximately 0.6. So once again, if I would like to conclude a full comparison of these two models, I would conclude that definitely this model is better, and not only better, according to my opinion, is also good enough to say, okay, it meets standards for structural equation models, as all these fit criteria we discussed are quite good enough. So if you compare two models, it's not enough to say that one is better, but you should also evaluate final model and to say whether it is good enough to use this model for the rest. And last one comment I would like to add to these comparisons is related to BICs and AICs, if they are present here in output. So I cannot see these values, so I can check it. Yeah. No, here it is not present. So maybe they are not by default outputs here. I will check it once again. So here we have only estimates, additional outputs. So AICs and BICs are not present here. So sorry for that. We wouldn't be able to use these for comparisons. So that's all for this comparison. And I guess we can skip discussion about residuals and modification indices. And I would like only to ask you, as we do not have enough time, that you should try also your own CFA practice, by example, based on UVS data. So there are 6 items, so you should take 2 factors, and you should try to decide whether correlated or uncorrelated factors would be better. And it's quite easy to guess that your last homework will be devoted to CFA. So I will once again prepare you description of this last one homework. And now we will switch into multiple groups discussion. So first of all, I will save our previous tasks. So I will only use a different name. So this is PCFA number 1. And before we start to compute results, so I would like to say some brief theoretical insight into measurement invariance or multiple group confirmatory factor analysis discussion. So first of all, this multiple group analysis has quite easy question behind. So the basic question is saying, can we apply the same model to different groups, for example, men and women, younger and older people, or people from different countries, etc., etc. So you can decide what's your intention for future to compare, and by this you would decide which groups will be compared by the quality of the model. So there are many different approaches by which you can apply comparison between individual groups in confirmatory factor analysis, but basic steps are usually based on chi-square test, but we know that this test is quite sensitive, so usually we do not apply these chi-square tests. And proposal from Cheng and Rensvold, the article was published in 2004, and it's a very, very influential article. And they proposed that we can compare CFIs for different models. We will discuss about these different models in a few minutes. And if the Cfi difference is below 0.01, so you can go to some slightly more advanced model for multiple group comparison. So that's Cfi difference logic based on the article of Cheng and Rensvold. So here it is. So that's the basic goal for multiple group analysis. So if I go back, for example, to my picture here, so here we have two factors, liberal, conservative, and left-right scale. And currently, we are using these measurements for all people enrolled in ISSP survey in the Czech Republic. So maybe I can ask whether I can apply the same model for Czech male and Czech female, for younger and older people, etc. So currently, we are only evaluating whether this model is measuring at the overall population, but maybe we would like to distinguish individual groups and to say whether these measurements are the same for groups or not. The main goal why we are trying to compare these models between groups is that if models for groups are comparable, then I can compare also, for example, left-right and liberal conservative level for different groups. If they are not comparable, so it means these measurement models, so this comparison would be totally useful, totally rubbish, sorry for that. So that's it. And now let's go briefly into the theory. I decided to use pictures for this description, so I hope it would help you to understand what is behind the scene. Then implementation in Chemovi or any other package is usually quite easy. So first of all, if we try to compare whether model is the same or not for different groups, we are mostly applying three consequent levels. And these levels are usually called, there are some different names, but mostly we are using names such as configural, invariance, on configural similarity, we can say, metric invariance or metric similarity, and scalar invariance or scalar similarity. And now we would need to understand what does it mean to have configural invariant, metric invariant, and scalar invariant data. And we would need also to understand what are consequences for file data analysis. So first of all, and here it is, these pictures are copied from the article which was published by Petra Nížová in Czech Sociological Review. So if you would like to know more about this problem, you can consult this article in detail. For those of you who are not Czech speaking, I would advise only to type measurement invariance, and you would find many articles all over the world. But these pictures are quite nice, and I didn't discover similar pictures in different in other articles, so that's why I decided to copy it from this Czech article. So here we have a very simple model for one latent variable, so one factor. On the left side and right side, we have group 1 and group 2. And this configural invariance, as it is written here in the subtitle, is expecting that I can apply the same picture for both groups. So it means that for both groups, it is valid that this factor is measured by three indicators, I1, I2, I3. So that's very, I would say, relaxed assumption. I'm only expecting that for both groups, and of course you can apply this logic to more than two groups, but two group case is the simplest, the picture is the same. So I am not constraining, as you can see here, some letters, any of these factor loadings. So these are small f1, f2, f3 for both groups. And I'm not also limiting, and it will be a new one step for today, these C1, C2, C3, which are constants or intercepts for these individual regressions that are behind the scene. So I'm saying, okay, in the first group, as well as in the second group, both pictures should be the same, but these factor loadings and these intercepts should be totally different from the next group. So I will apply only the same picture. So it means the same description of the model, but I will evaluate these individual factor loadings as well as these individual intercepts separately. So it means these values will be different between groups. So that's configurable invariance, or something what is called as the same pattern for the picture. If this configurable invariance is not good enough, so it means if I will try to evaluate this model, so it means I will divide data into two groups and I will compute two different models and then make overall evaluation. So then there is no chance to go further. So it means to advance the levels of invariance. We will be discussed in the next two slides. So that's configurable invariance. Here it is, so-called metric invariance. And I have here once again my subtitle, which is called equality of slopes. So if I would like to say that my data are metric invariant, it would need that these factor loadings and these factor loadings are both the same. That's why I added ellipses into this picture. So I'm not expecting only, as the first assumption, the same picture, but I'm also expecting that all these factor loadings are the same. If this metric invariance is valid on my data, so it means I would evaluate the model and I will make fixes that for the first group, F1 is the same as for the second group. For F2 the same, and for F3 the same. You know about these equality constraints from the previous discussion in regression as well as in path analysis. So only here we would not fix two parameters across one model, but we would fix parameters between groups. So if this model would be correct, it can cause that these latent variables could be applied into regression and correlation equations as their comparability is fulfilled. So that's metric invariance, equality of slopes. And the highest, or at least in classical style of measurement invariance, the highest level of invariance is called as scalar invariance. And here it is written that I expect not only same pictures, not only equal slopes, but I'm also expecting that intercepts, which was omitted from our previous computations at all, but currently it is necessary to add these individual intercepts. As here we have 1, 2, 3 regressions, 1, 2, 3 regressions, so that these constants or intercepts are the same across groups. And if this assumption is valid, so it means the same picture, same loadings, and same intercepts, then it is possible to compare the level of factor, so it means latent variable, for the first group and for the second group. If these conditions are not fulfilled, then if you would compare the level of the factor for group 1 and for group 2, you would be comparing totally incomparable concepts, and your comparison would be totally rubbish. So only if you go through these invariance steps up to scalar invariance, and you would find that scalar invariance is fulfilled, then you can compare these groups by the level of these factors. So that's the logic. So we would be evaluating first model, second model, and the third model, and we will be comparing these models. And usually, at least in classical statistics, we would be using Srmr and Rmsea recommendation based on Cfi difference, which should be as small as possible. And finally, what is also necessary to say, I'm comparing models. So this is nearly the same step as we were comparing previously, these two models. So not only I would be evaluating these models relatively, whether one is approximately the same quality, but we will be also finally evaluating final model, whether it is good enough according to Sem recommendations. So that's the step for this measurement invariance. And now we would go into Gmovie. We would open a new one data file, which is CASD8. So that's measurement of depressivity symptoms. These data, if I remember well, were collected at the beginning of the first phase of COVID pandemic in the Czech environment. So these data are based on university students and were collected, if I remember well, in May 2020. And we will try, first of all, to prepare this CSD8 confirmatory factor analysis, and then we will try to apply to this CSD data gender invariance comparison. So it means whether for male and female we can compare this model for depressivity. So it means whether we can also compare level of depressivity symptoms across gender. So here it is. So first of all, I would need to open data. I would go into open and find my data file. So once again, data are called as 11MI CSD8 SAV. So I will only close previous file for SSP CFA. And here we have the data. So here it is. The first variable is gender. So this is a variable which will be for us necessary for comparison of groups. I will only maybe redefine correctly that this variable is not ordinal, but it's nominal. And then we have the next variables that are called Q38A, B, C, D, etc., etc. And these are measurements of depressive symptoms. And if I remember well, the last one item is H, which is a set of CESD, which is a well-known scale for measuring depressivity symptoms. I will only try to briefly open data also in SPSS for you to see the scales start behind. I'm not sure if there is description. If not, I will try to find it somewhere else for brief insight into logic. So here it is. Yeah, there is no description at all, so sorry for that. So I will try to find some brief description of these scales very quickly. So I will try to find CSD description on my computer. Okay. So here it is. I hope so. Yeah. So that's some article about this CSD scale. And if I go down, we can see original items for this scale. So here it is. And there are answers ranging from 0, none, or almost none of the time, up to 3, all, or almost of the time. The question is about last week. And depressive symptoms are measured whether you feel depressed, you feel everything was in effort for you, sleep restless, happy, lonely, enjoy life, feel sad, and I'm unable to get going. Most of these items, 6 from these 8 items are negatively oriented, such as feel depressed, lonely, etc. But 2 of these, and it is item number 4 and 6, or in letters it would be D and F, is happy and enjoy life. So they are quite reversed. And usually, if you have some positive and some negative items in one measuring model, it is expected that you will be using correlations or covariances between residual errors for these items that are opposite to the rest. So I would expect here, and you can go down through this article, and I guess there will be maybe some picture, maybe not. Here it is on the simplest picture. So maybe it's not present here, sorry for that. Maybe yes, I will only make it small to see the whole picture. Yeah, here it is. And I guess that this is classical one-factor model for CSD8. And you can see that happy and enjoy life are expected to correlate these random errors. So that's why we would apply the same model. So we would take one factor and we would take a relationship for happy and enjoy life. Of course, not directly to these variables, but we will link these residual errors. So that's CSD 8 by practice. So I will close SPSS and once again go to Jamovi. We will try to apply Cfa model. So maybe we do not need to redefine scales of variables into continuous, as we know that in general Sem it would be necessary. So I would ask for factor and for Cfa here. So first of all, I would like to define that my factor will be called CESD8. And we would move 8 variables to the right window. So here it is. So it's defined here currently. And once again, we know from previous discussion, once again, here's the picture, that residual terms for happy and enjoy life, once again, that's item D and F, should be correlated. So I would go to the next dialog, which is residual covariances. And I would take D and F and move to the right side. By this step, I expect that the quality of model is increased. And here it is. So I would go directly to model fit. That's enough to additional output. And here I would ask for path diagram to see whether it works. And here we have the picture. So that's CESD 8 and item D and F are correlated by their random errors. Once again, this picture is slightly misleading as it is connecting directly items, but related are residual errors that are not present here in the picture. So that's the model. We will try to evaluate the model as a whole. So you can see CFI is quite nice, 0.975, TLI 0.963, RMSEA 0.07 approximately. So all of these criteria are quite nice. And for the next step, and unfortunately, we would need once again to go into SEM description. We would need to prepare this model. And we would need to add measurement invariance, which is unfortunately not present here. If you switch into JASP, into CFA clicking dialog, there is measurement invariance dialog here. For Jamovi, there is no such option. At least I will check it, but I'm sure it's not present here. Model fit, no, it's not present here. So sorry for that. For Jamovi, we would need some more steps. So I would go once again back into data, and we know we need to redefine scales for SEM dialog. So sorry for the next effort. So I would need to go into continuous for all of these. So here we are. So all these are redefined as continuous. And if I go back into analysis, so still we have the same results, of course, I would need to go into Sem syntax. And first of all, I would need to define my model as a whole. So I would need to prepare the model. So maybe I will once again use this Word document. So first of all, I will define CESD. Once again, I would need to define factor model, so equality sign and tilde. And then I need to add my individual variables. So once again, is Q, big Q, 38, underline A, up to underline H. So first of all, I would need to type this set of variables. So I would copy many times. I would only change letters, which are at the end. So B, C, D, E, F, G, and H. So that's our measuring model for CSD. So once again, I will copy it into the chat for you. If you would like to only make a copy. And if I go back, so here I would copy my model. And you know from previous discussion that we also connected random errors for these. And we need to also to assign it here by command. There is no chance by clicking here, as there is no dialog for covariance parameters. So I would need to type, and that's quite strange in Lavan, that Q48D should be related, so it means double tilde should be here, to Q48F. So it is the same condition as is present here. So random errors for D and F items should be related. So that's my second condition. Once again, I would copy it into the chat if you like to use it. And if I go back, so I would copy here into Chemovi. So that's my first step. And then I would go down. I would ask only for output options to see additional fit measures, as we would like to compare results for CFI, which is not generally present. And I can also ask for path diagram to check whether my model is defined properly. So path diagram, and ask for betas for simplicity. So here it is. And if you go to the last one, option for us important, which is multi-group analysis, I can define here which variable will be based for my multi-group analysis. So if I go back into data, so you can find very simply that my variable is called gender. So here it is. So I would need to type here in small letters gender. So factorial variable name for multi-group analysis must be here present. Yeah, you are correct. So you would need, sorry for that, it's Q78H last one. Yeah, sorry for that. So please change the last item. Sorry for that. I would need to go back, and here there is a double G, so H should be last one here. So thanks for correction. So here, factorial variable for multiple group analysis must be entered, and currently, I hope so, it would work, and we can compute the model. Oh, there is some mistypo still. Q38E is missing observed variables in dataset. So
I think it's called Q39, like it was in the picture before.
40?
39.
Yes, sorry for that. That's a mistake. Okay, so sorry for that. You can see that there is some mistake in my data. Sorry for that. It's not very easily to see. Yeah, it's Q39E, so that's mistake. Sorry for that. So I will change it. So as you can see, Jamovi is sensitive and all problems must be corrected. So Q39E, and now it should work. I hope so. So still not, at least I'm not able to see estimates. So missing value were true, false needed. Sorry for that. That's quite strange comment. I'm not sure what is Jamovi currently saying was the problem. So I will try to find it. So maybe I will try to cancel these blank spaces, but it should work, I guess. Once again. No. So sorry for that. It seems that Jamovi is not cooperating. I must admit that I didn't try to compute this model previously in Jamovi, so I'm not sure what is the problem. So I will stop this example, and I can promise that I will try to fix the problem and prepare you recording with solution. So sorry for problems that are present in Jamovi. I'm sure that these data are correct. They have no missing values at all, so it should work. But still, it seems that some problems are present here. So I would skip to the last one topic, and once again, I can promise that I will prepare your recording. For this case, once again, there is prepared your own practicing in Jamovi for intelligence data. So if you like, you can also try these models. And I will go briefly, at least we have 15 minutes, so it would be enough for the last topic. So I would be briefly discussing about latent growth models. So it means models that are prepared for longitudinal data. So if I observe repeatedly some phenomenon indirectly, I can somehow use also CFA framework, and of course I can use structural equation modeling software. Here I would switch, as I promised, to go to Amos as alternative software package. So first of all, I will go through the discussion of latent growth models, and then we will briefly compute our results. So latent growth models or latent growth curve models are designed especially for repeated observations. And ideally, we should have at least 3 time points or more for these models. So if you have only 2 points, it's useless to apply these models. So you can only compare results from the first and the second wave. So if you have 3 or more, it really matters to prepare models such as these latent growth curve models. I would like to say that if you have some repeated observations, classical approach in statistics is usually based on approaches that are called time series analysis. So this latent growth curve model could be seen as an alternative, especially in structural equation modeling, for these time series. And the logic is quite strange here, as dependent variable, or let's call it exogenous variable, sorry for that, not dependent variable, but unobserved variable should be written here, as you can see it here on the picture, is something what is quite strange. Here it is called intercept and slope, so it means it is intercept and slope. And I would like to use these variables for measuring the development of some phenomenon, which is repeatedly measured. So here I have a very simple case, and we will use the same example in my data. And I will be measuring 3 times some phenomenon, so that's x1, x2, x3. And I will try by latent variables, which are something like artificial, once again, intercept and slope, measuring the development and also the status in the first moment. So maybe I will slightly make bigger this picture to see details, as these details are really important. So here we have 3 repeated observations of some phenomenon. For example, in my data, I have 3 repeated observations for mathematics and science from 7th up to 9th grade at elementary school. And here we have 3 observations, and intercept, as you can see, is related to these individual observations by unit. So it means it is expected that there is some level at the beginning, which is also present in next 2 time points, and the development could be described by the slope, as here there is a length 0, here 1 and 2. So it means if I try to evaluate the mean level of this slope, I would get 1 year increase in, for example, mathematical or scientific skills of the student in general. So that's why I'm fixing these parameters into 0, 1, and 2 for slope to have possibility to evaluate development between years. So it means increases or decreases. Unfortunately, we are discussing, for example, about mathematics and science. So it means in Anglo-American style, some mixture of physics and chemistry. So if you go to 7 up to 9th grade, usually kids are not going up. Usually they are somewhere on constant level, or sometimes they are even decreasing. So maybe the slope could be negative here. And the last one, very important part of this latent growth curve model is here, that you can also expect, and by default you expect, that this intercept, so it means beginning level of individual kids, could be somehow related to their increase or decrease. So it can be, for example, that if somebody is better at the beginning, his or her progress would be bigger. Or just opposite could be true. So it could be positive or negative relationship. Or maybe there is no relationship, and then it means that increase or decrease for future is not related to the level at the beginning. So that's a latent growth curve model. Here by pictures, only you can see here some strange zeros. And these strange zeros means that also for this latent growth curve models, we need to include intercepts and means for computation, as we are mainly interested on the level of this intercept and slope. So we need means at least for these parameters. So that's about basic introduction into this model for development. We can apply, and I have 2 more pictures, if I remember well, in my presentation, some more advanced models for latent growth curve models. So we would go to the next 2 pictures. So here, for example, you have 2 models. Here is the one. Here is the second one. For example, here it would be for mathematics, and here it will be for science. And I can also make the link that I can expect that, for example, if somebody is better in mathematics, it could cause that somebody is better also in science. Also, the same could be for the progress. If I am improving in mathematics, I can be also improving in science. Maybe that these arrows should be also double-headed, as maybe there is no cause interpretation, but here we have only one-headed arrow for simple implementation. So I can make the link for different models for repeated observations by this style. And last one step, and that's classic in latent growth curve modeling. We wouldn't go into such details for comparison, for computation, but here we have, once again, classical model. So it means 3 time points and intercept and slope. But I would like to explain why there are some differences for individuals for their beginning level, so it means for the intercept, and why some kids are improving and some kids are maybe still stable or they are decreasing in their, for example, mathematical skills. So that's why I'm here, for example, saying, okay, for boys and girls, that will be different at the beginning. That's why I am here linking gender to intercept. Here, for example, I am linking type of school to the slope. So it means I'm saying that maybe in some schools there would be bigger increase, and for some there will be slower increase or even decrease. So I can add predictors to these intercepts and slopes, and you can see that also these predictors could be related to each other. So that's about these models. And now quick tour into IBM SPSS Amos. So I will try to open directly the model which is prepared for possibility to be quicker. So I need only to find once again for this course. Sorry for that. So here it is. And here we have, I hope so, Amos, which would be functioning. Currently, I'm opening the latest version of Amos. Amos is approximately last 10 versions, flowing versions of IBM SPSS statistics. So it means currently there is IBM SPSS statistics 28, and the same is valid for IBM SPSS Amos. So here you can see that here we have a predefined model, but I can show you that in Amos to define this model is very simple by this graphic tool. So I will click into File and New. So I have blank space here currently, and this is the space into which I can prepare the model. So you can see here some basic shapes such as rectangle, ellipses, factor analytic model, etc. So we can use these as well as one-headed, double-headed arrow, etc. But if you like choose some special models, such as, for example, latent curve models, there are some useful plugins. So I can go here into plugins. You click here into growth curve model. And if you say, okay, I have 3 time points and click into OK, so you can see that by default, Amos automatically will prepare you the picture which fits to your needs. And you will only need to assign data file and to say that X1 is, for example, mathematic grade number 7, grade number 8, and grade number 9. And then you can run the model. So that's very, very easy to prepare these specified models. Once again, here is the plugin for growth curve models, and that's very, very quickly and efficient. So I will take my model, which is already predefined here. I will not save this first. As in this model, there is already predefined that this is mathematic number 1, mathematic number 2, mathematic number 3. So it is related to data. I hope so. So all these properties are defined here. And if you like to run the model, it is enough to click into this calculation icon, and it should work. So in a few seconds, you would get results. And if everything is correct, there is active this red arrow, which is going up. And if you click into this red arrow, you can directly read results. And you can switch between standardized and unstandardized results. So maybe we didn't define standardized results, so I will change it. So here in analysis properties, I will ask for output and standardized estimates. So here it is. Sorry for that. I will save it once again, and I will run it once again. And here we are in output, and you can select unstandardized and standardized estimates with very nice pictures here. And all the rest, which is behind the scene, is output in text. So here we have a set of tables. And for us, the most important estimate here is the mean level of intercept and mean level of slope. And we are mainly interested whether kids from the 7th up to 9th grade are increasing or decreasing in their mathematical abilities. And if you go down here into estimates, so you can see it here that mean for slope is minus 0.175, which means that if you go from the 7th to 8th, from 8th to 9th grade, your capabilities in mathematics are decreasing according to these results. And you can also see very simply here that there is positive correlation between intercept and slope, approximately 0.3, which is saying, okay, if somebody is better at the beginning, he or she is increasing. But if somebody is quite at a low level at the beginning, maybe he or she could be decreasing. So that's also another important feature of this result. So especially slope level and this correlation is for these simple models the basics. So if you would like to apply this model in GEMO, VJESP, or directly in Laban, you would need only to prepare models. So it means that's one model for intercept, one model for slope, and you would need to fix these parameters as you can see it here. So all these links are 1, and here we have links 0, 1, and 2. And then you are mainly evaluating levels, so it means means for intercept and slope. That's the logic of latent closed curve models. So that's all for today, and I would only skip briefly the general structural equation models are usually a mixture of individual models we discuss. So here we have some general model, which is based on CFA here, and CFA here, and here it is something like regression, only a regression for latent variables. So if you go back here, you have separated pictures. So 3 CFAs, and here you have 1, I would say, regression for latent variables inside. And here is the complex model that you can evaluate. So the logic is very similar. I copied only as the last one slide here some real life example, which I computed in last years. So you can see here some 2 predictors and 1 dependent variable, and all of these are measured by many indicators. If you like to know more about this model, at least if you are Czech speaking, you can consult this model in detail in chapter 4 of a newly published book in which you can consult details. So I would like to thank you for your attention for today and also for the whole semester. And I would like only to say that sorry for today.